Hi there folks. Today it's my duty to try and prove to you the quotient rule in terms of where it comes from, rather than just presenting it to you in class from nowhere and saying, trust me, it does work, honest. So I'm going to show you from first steps and from first principles of differentiation where it comes from, so we can finally arrive at the well-known result, or hopefully well-known result, which is the quotient rule. So let's get straight to it and have a look at where it comes from. So, the proof of it. Before we begin with the proof of quotient rule, what we need to do is use a general result, which I won't robustly prove here, and essentially it's this thing. If you've got the limit of h approaching 0 of two differentiable functions, f of x and g of x, then as h approaches 0, we can take the limit of both the derivative function of f of x minus the derivative function of g of x, and the limit taken as one entity is actually one and the same as the limit of the derivative function taken as h goes towards 0, done separately, then minusing off the derivative function of g of x as two separate limits. So what I'm trying to say here is one limit can be split into two like so. So at university level or postgrad, this is proven in a much more in-depth way, but for now I'm just going to illustrate that it does make sense, it does work honest, by means of a quick illustrative example. So let's imagine f of x is 2x and g of x is x squared. Then from first principles, let's think about the derivative of f of x minus g of x. So it's as h approaches 0 of f of x plus h minus f of x all over h minus g x plus h minus g of x all over h. So if we input what f of x actually does, it doubles the input, and what g of x does, which is squares the input, we have this. We can now expand these brackets to arrive at this line. With some cancellations, we can see that this becomes just 2h over h, and on this line here we're subtracting off 2xh plus h squared over h, because this x squared cancels with this one. Dividing through by h, we get it's the limit as h approaches 0 of 2 minus, well in brackets, 2x plus h, so as h shrinks to nothing, the limit of both taken together as one limit is 2 minus 2x. So the red limit taken as 1 is 2 minus 2x as h approaches 0. Let's now consider this broken up into two separate limits. So first of all, the derivative function of f of x considered separately. So from year 12, this is the derivative function of f of x. If we plug in that f of x is 2 times x, we get this expression, simplifies to 2h over h. So it's the limit as h approaches 0 of just 2, which will just be 2 because 2 is a constant. And so the limit of f of x is 2. Now let's consider the limit of g of x and then subtract it away afterwards. So for g of x, it's essentially x squared. So g of x plus h is x plus h squared, minus g of x is minus x squared all over h. If we now expand these brackets out, we get this line, subtract x squared, so the x squared here cancels. We get this, and divide both top terms by h gives us the limit as h approaches 0 of 2x plus h, so as h shrinks to nothing, we're just left with 2x. And so the derivative function of g of x is 2x. And so the derivative of f of x minus the derivative of g of x gives us 2 minus 2x, which is what we wanted to prove. It's the same as the limit of f of x minus g of x taken as just one limit on its own. So taken as one limit, that's what we have. Split into two limits, we have the same result. So we are allowed to split the limit into two separate limits, which we'll use later. I'll mention when we use this fact. So now we've got that. In other words, the green limit minus the blue minus the green limit equals the red limit. As such, we can now move on with the proof proper. So this is quite in-depth and looks worse than what it is. So just bear this in mind. So from year 12, the definition of a derivative is as follows. We need to know this off by heart. So f dash x is the limit as h approaches 0 of f of x plus a tiny increment h minus f of x, all divided by this tiny increase h as h shrinks down to the limit of 0. So now let's use this same idea and introduce two new functions of x, call them u of x and v of x. Then in exactly the same way, u dashed of x would give us this expression, And v dashed of x would give us this here using the same definition of the derivative function. So instead of y, it's just u dashed and v dashed. Now let y be a quotient, basically one thing divided by another. So y is now a quotient of two other functions. So let y be big F of x, where big F is a quotient of a function u of x divided by the function of x, which is v of x. So split the page into two. Like I said, it's going to be lots of working here. So dy by dx, the derivative function from first principles, is this beast here. That should be no surprise yet. Let's now plug in, though, what big F actually is. So big F of x plus h would mean u of x plus h divided by v of x plus h, and minusing f of x means minusing u over v all over h. So we've got a fraction within a fraction here, but on the numerator, this fraction, these two fractions rather, do not have a common denominator. Here, one denominator is v of x plus h, over here another denominator is v of x. So let's try to obtain a common denominator by multiplying this fraction here by v of x, and multiply the fraction we're taking away by v of x plus h. So we get this here. This can then be simplified to this. So putting it all over the same denominator of v x plus h, v of x, we can just combine the first numerator, take away the second, like so. Now over here, what we can do, because we've got this denominator on the top, which is then being divided by h, we can simply say that the overall denominator is this vx plus h times v of x multiplied by h. So we're just consolidating this denominator divided by this one into just one single denominator. That's all we're doing in this step. The next step, which looks fairly awkward, but don't worry quite yet, is we're going to tactically add on to both sides ux, v of x, and then subtract away from both sides u of x and v of x. So this thing here is just for the next step. So this is just a stroke of genius, not mine. I wasn't one that discovered this. But this step here, by adding and subtracting the same thing, will allow us to nicely factorize in this step. So over here, we can factorize out v of x and factorize the u x plus h minus u of x away. So just to illustrate where we're getting those points here, I'm getting v of x, and I'm factorizing out from that the u of x plus h, and then minus this u of x from it. And in a similar way, we're minusing off u of x here. And so from that, what we're doing is minus u of x is being times by v of x plus h, which is this thing here. And then minus u of x multiplied by minus v of x is actually plus ux vx, which comes to this term here. So in green is what we're factorized into these brackets. So this here is just a factorization of this line. So just pause the video and get your head around that for a second before we move on to the next bit. Okay, so now moving on to the next line of reasoning, we have this. So as h shrinks towards 0, v of x plus h becomes one and the same as v of x. So this denominator becomes h times v of x multiplied by v of x, because x plus h approaches x. So v of x times v of x can be replaced with v of x all squared. So now I can then I can factorize out 1 over v of x all squared, just leaving here these two limits in red and in blue. So we've got the limit of vx times the derivative of the function u of x, minus away u of x multiplied by the function of v of x as h approaches 0. So next, what we can think about doing here is actually taking the v of x squared, the 1 over v of x squared, outside of the limit, because v of x squared here does not depend on h shrinking towards 0. So in terms of this limit, this is essentially almost like a constant. So that can be taken outside of the limit. The next thing we can do now is we can then split this limit into two separate limits using what we mentioned in the special case earlier in the video. So we are allowed to do that. Then we need to realise that we've got 1 over v of x squared on the outside. This v of x is just v of x, but this here, the limit as h approaches 0 of u x plus h minus u of x over h, that is the definition of the derivative of u of x. This is u dashed of x, and in the same way this limit here I'm going to put into green, that is the dictionary definition of the derivative of v of x. So in green this is v dashed of x. And so it all simplifies down to 1 over v of x all squared, vx u dashed x minus ux v dashed of x. Putting in a neater form with the vx squared underneath as the denominator, we have this here. And this is actually the quotient rule, which we've got now. So we now have the quotient rule. So if y is u over x, dy by dx is vx u dashed minus u v dashed all over vx squared. And this can be written in a few different forms, which I'm going to run through here with you. So the 3 main forms which I'm familiar with, and you will probably become familiar with, are these here. So dy by dx notation, function notation, and finally my shorthand version, which my teacher told me and it still sticks with me, like so. So these are all different ways of saying the same thing. So hopefully now you understand where the quotient rule comes from, which I'm hoping has given you an added dimension of understanding and hopefully enjoyment from the maths. But you tell me. Anyway, that's it from me. So once again, sincerely, thank you very much for tuning in. I hope you found some of it useful, and do stay in touch for the next videos in future. So take care of yourselves and be in touch in the future. Goodbye for now.